All right, so we are continuing section 8.6. Let me give you a moment to copy this example down. Okay, so let me ask, could we get the antiderivative? Can we get, let's see, this is the integral of the function x minus the arctangent of x over x cubed. Do you think we can get the antiderivative of that easily? Jacob says not easily. That's right. And it could be not at all even. You know, it's definitely not an easy antiderivative, and probably it's what's called intractable. It probably can't be integrated exactly. But we can utilize the power series, to help us. If we can express this integral as a power series, that's going to be very helpful, because, you know, for instance, we might want to evaluate the integral, hold on here, from, like, you know, negative, or like, you know, from 0 to 0.1, say. Maybe we want to evaluate this definite integral. Well, we can't evaluate it directly because we don't know the antiderivative of this integrand here. But if we could find a power series for the indefinite integral, we could substitute in the values of 0 and 0.1 into the power series and evaluate it just like we would a normal you know, antiderivative, you know, using the fundamental theorem of calculus. So what makes this problem difficult, would you say? What makes, like, what's the hard part of this integrand to deal with? The arctangent. That's right, Nicole. Well, what we're going to do is we're going to find a power series for the arctangent of x. Once we find that, then we can, through algebraic manipulation, we'll be able to come up with the power series for this indefinite integral. So here we go. What are we going to do? All right, here's the arctangent of x. Okay, here's the arctangent of x. And what I'm showing you is actually done in the book in example 7 from section 8.6, but I'm just putting in a little more detail for you. So we all know that the antiderivative of 1 plus x squared dx is the arctangent, right? Okay, and so again, you know, here's my formula. 1 over 1 minus the apple is equal to the power series n equals 0 to infinity of apple to the nth power. And of course, we require the absolute value of the apple to be less than 1. That's our interval of convergence. So I'm going to write the plus x squared as a minus negative x squared. And then I have the summation of negative x squared to the nth power after applying the apple formula above. And incidentally, my interval of convergence is going to be then, since the negative x squared, the absolute value of it's less than 1, that means x is between negative 1 and 1. But in order to make this useful, okay, in order to make this useful, we have to simplify what's inside here a little bit, you know, to make this integral useful. So the negative x squared to the nth power I can write that as negative 1 times x squared to the nth power. And I'm going to end up with the sum of, well, the infinite sum of a bunch of integrals. My terms are integrals. No, wait, hold on, I'm not there yet. So the integral of a sum is the sum of the integrals, right? Okay, just like the derivative of a sum is the sum of the derivatives, an integral of a sum is the sum of the integrals. And so I can bring the summation inside the series. If we look at this integral, and again, the integral changes with like the terms of your series now are all integrals, okay? And when we integrate with respect to x, how do we treat negative 1 to the nth power? Since we're integrating with respect to x, how do we treat the negative 1 to the nth power? We treat that as a what?
Constant.
As a constant. Good, Leping. Good, Nathan. So therefore, I can bring negative 1 to the nth power out in front of the integral. And then the integral of x to the 2nth power is just x to the 2n plus first power divided by 2n plus 1. And then we do have a constant of integration. It's actually, this constant of integration is equal to the sum of all the little constants of integration from each, you know, integral as n goes from 0 to infinity. So this is a power series then for the arctangent of x. Okay. But we do have that constant of integration. So I'm gonna try something here. I'm gonna try to solve for that c. Okay. So if we were to consider the arctangent of 0, okay, and we were to plug it in the series, okay, so the arctangent of 0, let me just try to get this a little bit nicer here. Okay, the arctangent of 0 is, okay, there, now, you know, so what I'm saying is when x equals 0, the arctangent of 0 would be this series where I put in 0 for x plus the constant. Well, what is this series going to equal when x is 0? What is the series going to equal? What's every term of the series going to equal?
0.
0, right? And so that's right, Maria, that's right, Nathan. And when you add up a bunch of zeros, you get 0. So what happens is you can say then that the arctangent of 0 is equal to a constant plus 0. But what's the arctangent of 0 equal to? Well, what's the tangent of 0 equal to? You remember what the tangent of 0 is 0, so the arctangent of 0 is 0. So we established then that that constant of integration is equal to 0. Because you see, it has to be, well, that's right, Nathan, but the constant of integration has to hold for any value of x you use. And choosing x equals 0 allows us to determine that constant of integration. It's really quite fascinating, but it's true. All right, are there any questions on that before we move on here? All right. Well, then we've established then that the arctangent of x is equal to this series. And if I can write out some terms of the series, and sometimes that's helpful to do. That's going to be helpful in this problem. Okay, so like how do I get this, the x here? How do I get that 1x, right? That's -1 to the 0th power times x to the 2 times 0 plus 1 power, all divided by 2 times 0 plus 1. That gets you 1x. The fourth term would be, hold on here. Yeah, fourth term would be -1 to the third, hold on. Yeah, to the third power. Okay, because we're starting at n equals 0. So n equals 0, n equals 1, n equals 2, n equals 3. Third term, fourth term is with n equals 3. So you have -1 to the third power times x to the 2 times 3 power plus 1, all divided by 2 times 3 plus 1. And hold on here, one moment. And that's going to give you the negative x to the 7th over 7. Okay, so just going to highlight those two. So, you know, nothing strange here, nothing strange. And it turns out that expanding this series out like I've done is going to be helpful for this problem. Because what we're going to do is we're going to actually take that arctangent of x in our integrand and substitute in the power series for the arctangent of x. But I'm going to write the power series, I'm going to write it in this format, where I list like the first 4 terms and then plus dot, dot, dot. I mean, we can do that. It's true. It's true. So what happens here is something nice happens. What happens in the numerator right here? What happens in the numerator? The x terms cancel. That's right, Nathan. That's right, Renad. They cancel out. And now you're left with this expression. But the x cubed in the denominator, we can divide that into each of the terms here in the numerator, right? And if we do that, we're going to get this expression at the bottom. So when you divide, you subtract the exponents, right? And so, yes, and then we get that expression on the bottom. Okay, please let me know if you have any questions. All right, I'll just kind of wipe. Rayon, how are you feeling about this? Okay, good, good, good. Let's see. Marcus, how are you with this? Are you comfortable with this so far?
Yeah, I think so.
Okay, step by step, very good. All right. V, how about you? Okay, good. Well, and now Renad is, okay, we're here. Very good, V. Excellent. So we're here now. And you know, now we want to get the antiderivative, but we really need to find a formula for this series. Okay, we need to find a formula. So let me show you how we do that. Let's go to the next page. So this is what we had, and it turns out, I mean, it's a series, right? So we're going to have, we can write, then we can go back to the summation notation, n equals 0 to infinity. And if I start my series at n equals 0, it turns out that this is going to be the pattern. How many remember the problems where, like with sequences, where you had to come up with a formula for the sequence of terms? Yeah, it's the same kind of thing here. It turns out that the denominator, well, let's just, let's test this formula out. Let's test the formula out. So let's try it. So, I can see 3, 5, 7. Okay, 3, hold on here, one moment. So that's skipping by 2's. So if I had 2 times 0, well, 2 times 0 plus 3, negative 1 to the 0th power, and then x to the 2 to the 0th power, that's going to get me 1/3, absolutely. And then the next term, negative x squared over 5, if I had negative 1 to the 1st power, x to the 2 times 1 power, and divide that by 2 times 1 plus 3, that'll give me negative x squared over 5. And then the final term, well, it is the final term, but 3 terms should be enough to hopefully pin down what the pattern is. If we have negative 1, see, the terms, since they go to positive, negative, you know you got to have like a negative 1 to the nth power, or the negative 1 to the n plus 1st power, something in there, right? And then the powers are even. You're going to have, you have x to the 0, which is 1, x. So in the terms of the series, you have even powers. So x to the 2nth power accomplishes that. If you had odd powers, you would have x to the 2n plus 1st power, for instance. But now this third term, x to the 4th over 7, okay, well, let's see, negative 1 squared times x to the 2 times 2 power, all divided by 2 times 2 plus 3. Yep, that gives me 7 on the bottom. So, definitely this works. And that's just a matter of practice, but that works. So now we have, are there any questions on this? It's like discovering. It's like discovery, okay? It's like discovering. It's like solving a little puzzle. But now what we have is we have the integral of the sum. Well, again, integral of the sum is the sum of the integrals. And again, since I'm integrating with respect to x, I can pull out the negative 1 to the nth power over 2n plus 3. I can pull that out in front of the integral. I can't pull it out in front of the sum because it's dependent on n. But with regards to the integral, negative 1 to the nth power divided by 2n plus 3 is treated like a constant because you're integrating with respect to x. And so what you're left with under the integral is x to the 2nth power. Well, the antiderivative is not hard on that. That's x to the 2n plus 1st over 2n plus 1st. So then this is going to be our power series for our indefinite integral. And I'll summarize this on the next page. But please let me know if you have any questions. Okay. Hey, give me a thumbs up if you're feeling comfortable. Okay, excellent. Excellent. Okay. Well, let's go ahead then. Excellent, excellent. Thank you, everyone. Well, then now let's go to the next page and sort of summarize this. So here was our series, and it starts at n equals 0, but and that's fine. That's an answer. But suppose that answer's not there in the multiple choice. Suppose you have a problem And you got multiple choice, you got 4 or 5 choices, and that answer's not there. Well, then you got to try some. Well, let's try changing the index to n equals 1 and rewrite the series. So if we're starting at n equals 1, if we're bumping up, if we're going up 1, then we have to subtract 1 off of everywhere we see an n. We have to subtract 1. So that's why you have n minus 1 everywhere there was an n. It's an adjustment because you're starting at the index is 1 higher than n equals 0. N equals 1 is 1 higher than n equals 0. So you have to then adjust your indexes to account for that. So that the terms of the series, no matter what the index starts with, the terms of the series all have to be the same. And so then we do a little simplification. 2 times n minus 1 minus 1, that's just 2n minus 2 plus 1. That gets you 2n minus 1, right? And 2 times n minus 1 plus 3 is 2n minus 2 plus 3. That gets you 2n plus 1. And there are no non-zero terms in there. So that is then the power series for this indefinite integral. And we can use the power series to like, for instance, we could, if we wanted to do the definite integral from 0 to 0.5 of x minus the arctangent of x over x cubed dx, then this power series will work. It'll work fine. But if we wanted to do the definite integral of 0 to 1.5, okay, the definite integral where our limits are from 0 to 1.5, that we can't do using this power series. Why is that? What's the problem?
It's not in the convergence interval.
That's right. The first integral is good. Maria, what's not in there then? You say a second integral won't work. Can't use the power series to help you. Why is it not inside? Can you tell me? Can you be more specific?
Didn't you say that the interval was negative, but x between -1 and 1?
That's correct.
So 1.5 is greater
There.
than 1, so
There
therefore
you go.
it won't work.
Excellent. Excellent. That's right. Okay, are there any questions on that? All right. Let me bring up the ebook for a moment. One moment here. Okay, let me bring this up here. So section 8.6 has a lot of nice examples. And they have some formulas. So like, for instance, the formula we derived, the power series for the arctangent of x, they have that in section 8.6. And here's another function, the log of 1 plus x. We'd like to know the power series for that. And they derive that. So remember, you'll have access to those formulas on the final exam. As you know, you'll have access to those formulas. So you don't need to remember them, okay? But we're going to use them for the next example. So like this one here, the next example, I want to make use of this power series for the log of 1 plus x. And incidentally, the interval of convergence is the absolute value of x is less than 1. And, it makes sense. It makes sense. Well, again, to show that, you'd have to, you'd have to look at the derivation above. But let's go ahead and get to the example here. I want to get to this example. This is such beautiful stuff. I mean, how many are thinking this is like the coolest stuff I've ever learned in math? Does anybody have that thinking right now, that this is like really? Well, I hope I get some more positive response. Okay, good. I need something for my recording here. Thank you, Nicole. Thank you, Jacob. I mean, it's new, and you might be a little nervous about it, but it's going to be fine. It's going to be fine. All right, so hold on now. Where's my thing here? All right. Get this off here. So important, this material. Okay, let me give you a moment to copy this example down. Okay, so here we are. Does anybody know offhand the antiderivative of the log of 1 plus x to the 4th power? Does anybody want to try to get that antiderivative? Or who would prefer to, hey, let's use a power series? What do you think is going to be a more fruitful endeavor? The power series. That's right, Nicole. Okay, now we want to approximate this integral correct to 6 decimal places. And you've had some experience with this, approximating series correct to a certain number of decimal places. So the first thing we need to do is we need to find the power series for the log of 1 plus x to the 4th. So it can be shown Well, first of all, it can be shown that, and you saw it in the ebook, that the power series for the log of 1 plus x is the summation where n equals 1 to infinity of negative 1 to the n minus first power times x to the nth power over n. And x is between where, and that's true when you're for x values between negative 1 and 1. Well, therefore then, the log of 1 plus x to the fourth power, we just x to the fourth, you know, that's our apple. Okay, that's the apple. That's the apple, right? You just substitute it in, and you will get this series here, the series where n equals 1 to infinity of negative 1 to the n minus first power times x to the 4nth power divided by n. And same interval of convergence, x is between negative 1 and 1. And given that our integral, the limits are from 0 to 0.4, this is going to be fine, what we're doing. So the integral of the log of 1 plus x to the fourth dx is the integral then of this power series dx, right? But the integral of a sum is the sum of the integrals. And so that gets us down here. Please let me know if you have any questions.
And nothing can be brought outside the interval because they all have n in it, correct?
That is, well, the negative 1 to the n minus first power, that can be brought in front of the integral. That could be brought like out here in front of the integral, because since we're integrating with respect to x, and the n too, those terms, the n and the negative 1 to the n minus first power, they can both be brought out in front of the integral.
Oh, right, because you're integrating with respect to x and not n. Even, okay, gotcha.
That's correct. Okay, are there any other good questions? All right, well, let's proceed on then, and you know, we have to integrate, right? We have to do that next, and so okay. So I did bring out the negative 1 to the n minus first power over n. I did bring that out in front of the integral. And now the integral of the antiderivative of x to the 4nth power is short, Marcus. Short. Let me go back for a moment, class. Let me know, y'all, when you're ready. Okay, good. Thank you, Marcus. And how about everybody? Are we all good? Maybe give me a thumbs up. Okay, excellent. Okay, well, very good. Okay, well, so now we bring the again, we bring that negative 1 to the n minus first power and the n. We bring those out in front of the integral, and then the antiderivative of x to the 4n power is just x to the 4n plus 1 over 4n plus 1. And so, and then of course we do have the constant of integration, right? So now we have our power series here for the integral of the log of 1 plus x to the fourth dx is equal to this power series. And of course, x is between 1 and -1. I'll put that n equals 1 back. Just give me one moment here. Okay, so now I'm not going to worry about solving for that constant c. I'm not going to worry about that constant of integration, because I'm doing a definite integral, right? I'm doing a definite integral. So all I need are the terms of the series. So what I'm going to do is I'm going to write out the first 4 terms of the series. Okay, I'm going to write out the first 4 terms of the series. And so naturally, the first term is when for n equals 1. Second term is when n equals 2. See, to evaluate, I have to put some terms of the series down, right? Third term is when n equals 3. And the fourth term here is when n equals 4. Okay. Okay, and so what I do is I'm going to be like a fundamental theorem of calculus. I have to put in the 0.4, and if I put in the 0.0. So I first put in 0.4 into my power series, and I have I'm going to do it for the first 3 terms, and then when I put in 0 in the power series, I just get a 0, right? So that's like minus a 0 there. Okay. What kind of series is this? What kind of series is this here? Alternating series. Okay. So that's right, Renat. So that means we can make use of the alternating series estimation theorem. Okay, the alternating series estimation theorem. We can make use of it, right? From section, hold on here. Just get that 5 to show a little better. Yeah. Alternating series estimation theorem. So the alternating series estimation theorem tells you that, well, first of all, we want an answer correct to how many decimal places? 6. So that means the standard the standard I'm looking for is, if I'm, hold on here, one moment. One moment. It'll just come off, hold on. So the alternating series estimation theorem, you learned that back in section 8.4. And we are requiring that the estimate of this definite integral, that it be accurate to 6 decimal places. Okay, and therefore 5 divided by 10 to the 7th power, because 7 is 1 more than 6, is what is the what's the word I'm looking for? It's the criteria that we're looking at. So what I do with the alternating series estimation theorem is I write out the values of each term. So the first term is 0.002048. Is that less than 5 over 10 to the 7th? No. As a matter of fact, just to kind of help you here, 5 over 10 to the 7th, 5 over 10 to the 7th is 0.1234565, right? It's yeah, let me see here. Tenths, hundreds, thousands, 10,000s, 100,000s, millions. It's 5 10 millions. So what we do is we say, okay, using the alternating series estimation theorem, I'm going to enumerate the values of my series, and I'm going to stop once I reach a term that is smaller than 5 over 10 to the 7th power. First term is not smaller. Second term is 0.0000146. That's not smaller. But when I get to the third term, I have, which is 0.000000172. That's smaller than 5 over 10 to the 7th power. So that tells me then, by the alternating series estimation theorem, that I only need the first 2 terms of this series. The sum of the first 2 terms of the series will give me an estimate that's correct 6 decimal places. Okay, that's what it says. How many remember the alternating series estimation theorem from section 8.4? Okay, good. I hope you'll remember it. It's on, okay, good. It's, you know, on part 2, right, of your exam. So, are there any questions before I go to the next page and to finish up this example? And you can understand with the alternating series estimation theorem that if this third term here, if this third term is smaller than the error that we want, then that third term and all the remaining terms here are you know, the remaining terms are not going to increase that value at all, you know, because you're doing plus, minus, plus, minus, plus, minus, and the terms are getting smaller and smaller. So you're good. Okay, are there any questions? All right, let me know when I can go to the next page, when I should move to the next page. Okay. Maria's good. Nicole's good. Tall's good. All right. Gloria, how do you feel about this? Are you okay with this? Are you comfortable with this material? Good. Iker, what about you? How are you? Excellent, Gloria. What about you, Iker? Okay, good, good. Baraka, how about you? All right. Well, let's see. Michelle, how about you? You're feeling all right with this? Good, good. Okay. Well, then let's go ahead then and summarize the problem on the next page. By the alternating series estimation theorem, okay, this definite integral is going to be approximately equal to 0.4 to the 5th power over 5 minus 0.4 to the 9th power over 18. And that gives us 0.002033. And that should be correct 6 decimal places. And if you work it out like in Desmos or the TI calculator, you're going to have, let me just see one thing here. Yeah, you're going to have agreement to, you're going to have that kind of agreement. Let me just see one thing here. I mean, you know, Jeff Bezos wouldn't have gotten to the moon without this. I can tell you that, right? Or not the moon. He went like not into outer space, but kind of on the edge of outer space. Is that right? Jeff Bezos,
Past the Kármán line.
I'm sorry, Maria, what?
Past the Kármán line.
Past the Kármán line, okay. And we all helped him, right? Because we buy stuff from Amazon, right? So, all right. They're hoping someday maybe like, you know, anybody could go up there, but I think right now it's what, $220,000 or something to like for a ride. Is that right? It's my I don't know if anybody heard it. It's not cheap, right? It's not cheap, you know. I kind of like being on Earth right now, I'll tell you. But who knows, someday in the future. Are there any questions at all? Nathan's not in the market for it. Okay, Nathan's going to spend his money in other ways. Okay. All right. Who's feeling reasonably good here? Maybe give a thumbs up if you're. Okay, excellent. Excellent. Good to hear. Good to hear. Wonderful. All right, I'll stop the recording. Yeah, Maria mentions Wally Funk. I don't know who Wally Funk is, Maria. I guess I should know. He went up with Jeff Bezos.
She was a female astronaut that wasn't able to go up on, I think it was the Mercury 13.
Oh, it's a she. Okay.
Yeah.
See, I haven't been following the news too closely on this.
So she finally got to go.
She got to go up then. That's great.
Her mission got scrapped. She was with a few other female astronauts. They weren't able to go, so she finally got to go.
Okay, wonderful. Did Bezos maybe pay for her? Did the government did she? Well,
I think she was chosen. I don't know. I don't know specifics, but I just think it's really cool.
Well, and being she's an astronaut already, it's a good choice. All right, and good for her. Good for her. Excellent, excellent. Okay, I'll stop the recording.